Hey audience, last time I made a set of Napier's bones, which helps you do multiplication more quickly. There are other things you can do with them, but
that's alright, we'll worry about that later.
There was a step in using the bones for multiplication that was a bit more time-consuming and error-prone than we would have liked. Let's say we wanted to multiply the numbers 3,224 and 9,017. The first step is to copy down the rows from the bones onto a new grid. We'll take row 9 and copy that down, which has 2, 7, 1, 8, 1, 8, 3, and 6. The 0 row is all zeros, so we'll just ignore that and leave those blank. In the 1's row, the carry digits are all 0, so we'll ignore those and just copy down 3, 2, 2, 4. And then we have the 7 row last with 2, 1, 1, 4, 1, 4, 2, and 8. Now we add along these diagonals. So here we have 8 and a 10, so carry over to the next row. That gives us 8, then 10, so carry again, then 17, so carry again, then 10, another carry, and then a 9, and then a 2. So we end up with 29,070,808. The problem is that it takes a long time to write down these rows, and they don't line up properly if you don't write them out well like I did, and it's easy to make mistakes while copying. So I wonder if we can do something better than this. Wouldn't it be nice if we could just take a snapshot of these rows, then cut them out and rearrange them instead of having to rewrite them over and over again? So one thing we could do would be to make strips of paper that have rows cut out of them, and then each of those will isolate a single row of Napier's bones. And then we just have a separate cover sheet or mask for each digit that we want to multiply by, and that will uncover only the row that we care about and cover up everything that we don't. And that essentially gives us a copy of whatever row we want to use. But we want to multiply by more than just one digit at a time, so what do we do then? Why don't we just make our bones longer? We can have multiple copies of each bone laid end to end, then we can lay out our cover sheets in the order we want, as long as you don't run out of bones like I did here. So these rows do line up with the rows that we want to copy down, and they are in the right order, but they're pretty far spaced out. So our problem here is that our bones are too long, and it would be nice if we could make them wider and shorter by moving some of these entries up to the side. It would be best to make them square, since that would balance the size between the width and the height. So each bone has 10 entries, multiplying by 0 through multiplying by 9, and each entry has 2 parts, a unit and a carry digit. So let's say we wanted to make each bone square. It's easy to divide a square up into 9 pieces. Here we have 10 entries, but you'll notice that whatever bone we have, the multiply by 0 entry is always just zeros. So we can just ignore that entry and use a cover sheet with no holes in it to represent multiplying by 0. So we'll lay out our entries, multiply by 1, 2, 3, etc. So we'd have 4 times 2 here, and 4 times 3 here, etc. So then our cover sheets can have holes in them that will reveal whatever entry that we need. So now we have a square Napier's bone that's copied 4 times, and each one is just all the entries except for multiply by 0, wrapped around into a square. So now we can line up our bones as we did before, and then our cover sheets now have holes instead of slots, so that they can cover up everything except the entries that we want. And our multiply by 0 cover sheet has no holes and covers up everything. And now this ends up looking exactly like the rows that we copied down earlier. The problem is that they're all a bit wonky and not lined up quite right. What we really want is for each of these squares, the bone with the cover sheet on top, to look like a large version of the square entries that we copied down earlier. So it would be nice to have a diagonal line through each square with the units digit showing up below the diagonal and the carry entry showing up above it. So let's take a look at how we can do that. So we can say that each bone has 9 entries, and each entry has 2 triangles in it, with one triangle being the units and one triangle being the carry. But what if we took each and split it, and then put the units into the bottom 9 triangles and all of the carries onto these top 9 triangles? And then instead of having a square hole on the cover sheet, we can have one triangle hole on the bottom to reveal the units digit that we want, and one triangle hole on the top to reveal the carry digit that we want. So each entry is split into 2 sides. So once we split it up like this, we can draw a diagonal line down the middle of the cover sheet, and we can treat it like 9 carry entries on the top and 9 unit entries on the bottom. So we can put the multiply by 1 carry here and the multiply by 1 unit here. Then we place the other entries wherever we want, as long as we're consistent, and put the units on the bottom and the carries on the top. And then our cover sheets have 2 triangular holes in them, one above the diagonal and one below. So when we put it over the bone, the whole thing looks like a single square from the lattice multiplication method that we did earlier. So now we have these new sets of bones that we can lay out, and these cover slips that we can lay out on top of them, and it ends up being very usable. The way things are lined up makes it very easy to add up along these diagonal groups. But let's see if we can make it even better. When we made these original Napier's bones, we made them two-sided so that we could have more bones. So that'll be easy enough to do with the new bones, but wouldn't it be nice if we could do something similar with these cover sheets? So notice that when we flip over these cover sheets, the diagonal lines and triangle holes don't line up the way that we'd like. But if we rotate by 180 degrees, then we can see that diagonals still line up the way they're supposed to, and any triangle holes from the bottom end end up on top, and triangle holes from the top end end up on the bottom. So maybe we could use each cover slip for two numbers, one for each orientation. It would be nice to have numbers on each orientation of any given cover sheet to add up to 9, since that would make it easy to find any number you're looking for, even if you can only see one side for whatever reason. But we run into a problem with that pretty quickly. If the numbers on each side add up to 9, the 9 cover sheet would need to also be the 0 cover sheet in the other orientation. Any digit multiplied by 9 will almost always have a carry digit, so the 9 cover sheet definitely needs two triangle holes. So whatever way it's rotated, it will show some numbers, but the 0 cover sheet needs to never show any numbers. There is a solution though, which is to put the 0 and the 1 cover sheets together. Notice that any digit multiplied by 1 is never going to have a carry digit, so we don't actually need two triangle holes on the 1 cover sheet. Now we can see that if we flip over the 1 cover sheet, none of the unit entries are exposed anymore. So that gives us our 0 units digit for the multiply by 0 cover sheet. There will be an entry on the carry side open, but since the multiply by 1 entry on each bone is guaranteed never to have a carry, that means we're guaranteed to have at least one unused carry entry on each bone, which we can just assign to the multiply by 0 cover sheet and then leave a blank. So that lets us use 1 and 0 together on the same cover sheet. But how do we make this work with all the other cover sheets? What we can do is we can treat 0 as though it were 10, and then instead of having the numbers on each side of the cover sheet add up to 9, we can make them go up to 11. So 9 matches with 2, 8 to 3, 7 to 4, and 6 to 5. Then they still all have numbers on each side adding up to the same number, so it'll still be easy to find one number given the number on the other side of the cover sheet. Now that we've planned out which numbers to put on each orientation of the cover sheets, how do we know where exactly to put all of the unit entries, carry entries, and the cover sheet holes so that everything works? Let's start by only worrying about where to put the units entries on the bones. Let's lay them down in some arbitrary order that looks like it makes a little bit of sense, like this, which is just sort of in order from top to bottom. Now we grab a blank cover sheet. In this case, we'll just call it the multiply by 9 cover sheet, and then we'll cut a hole for the units digit since we've already planned out where that will go. Now we can rotate the cover sheet, and that makes it the multiply by 2 cover sheet, because we've decided that 2 goes with 9. The hole that we just cut out must then be the carry digit for the multiply by 2 cover sheet. And since we already planned out all the units digits, we know where to cut the hole for the unit portion of the multiply by 2 cover sheet. Once that hole is cut out, we can rotate it back around to the multiply by 9 orientation, and the second hole that we just cut out then becomes the multiply by 9 entry carry digit. We can repeat this process until we've mapped out all the carry digits. Let's do a multiply by 3 next. The units hole goes here, then we rotate it around and find the place where the multiply by 8 carry goes, cut the multiply by 8 units hole, and then rotate it again to find the multiply by 3 carry location. Then multiply by 4 cover sheet. We cut the units digit hole, rotate and identify the multiply by 7 carry location, cut out the multiply by 7 units hole, and then rotate it and identify the multiply by 4 carry location. Then multiply by 5. Cut the units hole, rotate and find the multiply by 6 carry location, cut the hole for 6, then rotate and identify the carry location for 5. That just leaves us with our special case, the multiply by 1 and multiply by 0 cover sheet. We'll cut out a hole for the units portion of multiply by 1, then rotate it to make sure that the carry portion of the multiply by 0 entry is empty. And then we're all done. Now that we've found out where to put the holes, the unit entries, and the carry entries, we just have to make the new two-sided bones and cover sheets. And there we have it, a set of thick Napier's bones that are divided up in a weird way with a set of cover sheets that just so happen to reveal the right numbers in the right places to make the whole combination look just like a larger version of our lattice that we use to multiply. Everything is lined up by these diagonals, and we just add. Easy. The name Promptuary comes from the Latin word promptuarium, which is a place, that's the areum part, where things are kept for easy access or quick use. That's the prompt part. So the name seems to refer less to these strips and cover sheets and more to the box that they came in, which I think is kind of interesting. There's one more interesting mechanical computation device that Napier invented and published at the same time as his bones and Promptuary, called location arithmetic. It's a bit cumbersome to use, and I think it might have been used less often, but I honestly think it's the most interesting of the three, and I'll talk about how it works and why I believe it's severely underrated in the next video. I'll see you then.
I will see you there.